I'll do the introductions for the speaker today for the first session of this afternoon. Dr. Bill Chadwick is a research professor in geology and geophysics at Oregon State University's Hatfield Marine Science Center over in Newport. So he drove over this morning. Bill studies undersea submarine volcanoes and associated hydrothermal vents using advanced sonars, monitoring instruments, and robotic underwater vehicles. He's led many research expeditions to active volcanic seamounts offshore of Oregon and in the Western Pacific. He'll talk today about the undersea volcano called the Axial Seamount off of Oregon's coast. So let's welcome Bill.
Thank you. Thanks for coming. All right, so how many people have heard about Axial Seamount in the news this year? Yeah, it's been in the news. So I'm going to tell a little story about all that. So this started last December. I usually go to this science meeting called for the American Geophysical Union. So in December, they had their annual meeting in Washington, D.C., and I gave this talk about how Axial Seamount was perking up. We've been following it for many years, and you know, I do this every year, so it's no big deal. I kind of give a status report on what's happening. But there was one reporter got interested in the story and wrote an article in Science News, which is a weekly news science magazine. That we thought it was going to erupt by the end of the year, and somehow that started this media snowball that is hard for me to understand. But so it was picked up by the Portland media stations, and then there was a front page story on the Oregonian. This was in December, January, and the way it sort of went from the sublime to the ridiculous. So is there going to be a disaster? The first few stories, the reporters were actually really good. They interviewed me. They weren't in a hurry to publish something. They got the story right. But then once it's out there, it's sort of turns into the Wild West, where other people report on it without really worrying about the details. And even popular mechanics got into it with it's going to blow. So then this was, December, January, kind of ran its course, things calmed down. But then one of the reporters I talked to in January didn't get around to publishing their story until May. So then there was a second snowball that started with this story. And the national news, at least websites, and even made the front page of the LA Times. This was in May. So, and again, the reporters that weren't in a hurry, pretty much got the story right. But then there's this whole other aftermath. So, and in today's world, some stories are written by AI. So this was one, and they even generated an AI-generated image of. This is supposedly what Axial Seamount looks like, complete with tropical fish. So, and the ultimate was this. This was the End Times News. This is a Facebook group that is trying to predict the end of the world, I guess, and they reported that Axial Seamount had erupted in July, but it was, completely made-up story. They also had an AI-generated picture, but for some reason they qualified that the story was bogus, but the image was made up. So anyway, so I'm going to give you the straight dope of what all this commotion is about. So Axial Seamount is a hotspot volcano. It's superimposed on the Juan de Fuca Ridge offshore Oregon. So it's about 500 miles offshore due west of Astoria. This is our tectonic neighborhood offshore. So there's the red line as a plate boundary where the plates are spreading apart. And the dashed line here is the Cascadia subduction zone where we worry about the big earthquakes along the coast. So they're pretty far apart. And down there at the bottom is the Blanco transform fault. That's kind of like the San Andreas fault where the plates are slipping by each other. So we have these three different ways that plates interact, tectonic plates. So in cross section, it looks something like this. Off to the left there is where the plates are spreading. The mantle is upwelling there and generating magma, which feeds volcanism. So all up and down the Juan de Fuca Ridge, there's submarine volcanism because the plates are spreading. Then on the kind of right is where the subduction zone is. That's where the plate is going under North America. That also generates magma that feeds the Cascade volcanoes. So we have volcanism on both sides, but they're very different character. So why study axial seamount? Well, it's the most active volcano in our neighborhood. Because of this hot spot that's located underneath it, it has a pretty robust magma supply. So if it's not erupting, it's getting ready for the next one. For a volcanologist, we learn the most about how volcanoes work by catching them in the act. So this is a great place for studying volcanism in general. It's because it's on the spreading plate boundary, the crust is very thin. So it's kind of has a very simple structure and is a great study area for testing ideas about how magma is supplied and how eruptions are triggered and so forth. So we've tried eruption forecasting out there in an area where we don't have to worry about alarming people because nobody lives there. So we don't have to worry about the societal impacts except for getting it wrong, but that's okay. And it's also monitored by something called the Ocean Observatories Initiative that has a cabled observatory out there. So there's a cable from Pacific City that goes all the way out to Axial Seamount. A bunch of sensors are plugged into the cable. So we actually have real-time data from this submarine volcano way offshore. And most of Earth's volcanism actually occurs in the oceans, but it's far away from all the sensors on land, so it's difficult to detect and know when things are happening. So axial is an exception to that rule because of this cabled observatory. So it's a chance to learn about this fundamental Earth process that we don't know that much about. So there's lots of ways of monitoring volcanoes on land. I'm going to talk a lot about ground deformation. It's basically the idea that the surface of the Earth moves at volcanoes because of the magma movements underground. And by measuring those things on the surface, we can try to figure out what's happening underground where we can't see. So here's a little cartoon. Volcanoes like Axial have some sort of magma reservoir underneath them. And these things, the magma is pretty fluid. So as magma is supplied to the reservoir, the whole volcano kind of inflates like a balloon. And so it pushes up in this case, the seafloor above the magma reservoir between eruptions. And then during an eruption, a crack opens up, a bunch of that magma that was stored erupts onto the seafloor, and so it goes back down. So there's this slow inflation between eruptions and the rapid deflation during eruptions. And so volcanoes like Axial around the world are like Kilauea volcano in Hawaii or Krafla volcano in Iceland. The magma composition is basalt, it's very fluid. So these are volcanoes where the eruptions are fluid lava coming out, not big explosive eruptions like Mount St. Helens. So at volcanoes like this, these are on land, of course, this inflation-deflation cycle sometimes can be very repeatable. So on the top here, there we're measuring the ground moving up in meters, about a meter. So there's this sawtooth pattern. So it's gradually rising between eruptions or intrusions in that case, and then rapidly going down and repeatedly. So you get the idea that if this pattern is kind of the same each time, then as it's inflating towards the next event, you can try to anticipate when the next one might occur. So we've tried to do that at Axial. On land, these kind of measurements are made with GPS or tilt meters or leveling or radar from satellites. None of those things work on the seafloor. So instead, we've adapted very precise pressure sensors that we put on the seafloor that were created for other uses, but we're using them to see vertical movements of the seafloor. So if the seafloor goes up, it's measuring the pressure from all the seawater above it, right? So if the seafloor goes up, there's a little bit less pressure, and we can actually measure that with these sensors. And same thing, if the seafloor goes down, there's a little more pressure. So, and these pressure sensors can measure about a centimeter of vertical movement. So kind of amazing. Okay, so we have this, we started making these measurements way back before 2000. And one was put out at Axial and happened to catch an eruption back in 1998. So this plot, we're looking at vertical movements of the seafloor in meters. So that big drop that you see is over 3 meters. That's like 10 feet. That's huge, big signal. And then there was we measured this, but we really weren't organized to keep this going. It was kind of a surprise, but within a couple of years, we developed a technique to measure the reinflation. So these, the blue line is continuous pressure measurements, but those instruments have a drift. And so there's also these purple dots that are another way of measuring the same thing, but is a way we can take out that drift. So that's just, those things go together. So, and at this time, these were before the cable was out there. So these are instruments that we put out. They recorded internally, battery powered, and we don't get the data back until we get the instrument back. So every couple of years we get two years of data. So, and about this time in 2006, we could see we were measuring reinflation. And because of that data gap, we didn't know exactly how those things aligned with the signal in 1998, but we could kind of eyeball it. And even then, we were thinking, okay, well, if maybe this is a repeatable pattern, what would that look like? So, and maybe it's going to be ready to erupt again when it gets back up to the same level it was at in 1998. So we made this broad eruption forecast window from there and just decided to see what would happen. So it turns out that's pretty much what happened. It's kept inflating at about that same rate, and then it erupted again in 2011. So hey, that kind of worked. So this time it deflated a little less, and right after that eruption, it was reinflating. The rate of reinflation was greatly increased. So it was going back up much more quickly. And again, we were only getting data every 2 years, so we got till there. And then we had another technique that told us that it was kind of continuing at the same rate. And so, but this time, since it was inflating faster, there seemed like there was less uncertainty in terms of time. So we made another forecast this time that it would erupt sometime during 2015. Hey, it worked again. How about that? So that got us pretty confident. Maybe this is a pretty regular, repeatable, inflation predictable system. So before I continue that story, I'm going to take a little side trip about what these eruptions look like. So we're going to talk about the 2015 eruption. So there's Axial Seamount in the middle there. You can kind of see this linear thing that's going from the bottom to the top. That's the Juan de Fuca spreading ridge. And Axial actually has a south rift zone and a north rift zone and a summit caldera. That's that crater that's in the middle there, in the middle of that red blob. And so the one rift zone goes to the south, one rift zone goes to the north, sort of parallel to the ridge. So magma is stored beneath the summit, and when it erupts, let's see if this is going to go by itself. Yes. This is an animation that shows 3 or 4 cross sections made by seismic data that are kind of like doing an MRI in your body. So we're trying to see where the magma is underneath the seamount, and there's this big blob that's about half a mile down, a kilometer down or so. And with the seismic data, they can speculate about what parts of it have more melt or less melt. But what happens is so magma accumulates, the pressure builds. Eventually, it overcomes the strength of the crust above it. A crack opens, and magma is intruded up that crack that opens up on the seafloor, and lava flows flow out from this fissure that opens up. So if there wasn't all that seawater in the way, this is sort of what it would look like. This is an eruption in Iceland. So this is the same sort of process where a magma-filled crack propagates from the magma reservoir beneath the surface up to the surface. The crack opens up, all this pressurized lava gets squirted out like in a big fountain, and that feeds lava flows that spread out to either side. So these are the 3 eruptions that have happened at Axial in the last 30 years. 1998 on the left, the black outlines are the lava flows that formed, and the red lines are the eruptive fissures, the cracks that opened up. So in 1998, it was started in the caldera, went a little bit south. In 2011, same thing happened, but you can see at the bottom there was a big lava flow way to the south, so that crack propagated like 30 miles south and fed lava flows down there. And most of the lava came out at the south end. In 2015, it went north instead of south. So again, it started in the caldera. The lava flows near the caldera are quite thin, so they didn't last very long. And then the flows at the northern end are the biggest in volume and the thickest. So most of the lava came out at the northern end of that crack. These magma-filled cracks are called dikes. That's what geologists call them. So we're kind of looking parallel to the axis of the ridge, perpendicular. So there's the magma storage areas under the summit. During these eruptions, the crack opens up these dikes, and it either goes north or south, and to feed eruptions along the length. And then to find out what happened, where the lava ended up, we have to go out there and remap the seafloor because it's a big area. It's almost a mile deep. It's really dark, so you can't just wander around and look for it. The most efficient way is to remap the seafloor with sonar, and if the flows are big enough, you can see depth changes where the lava came out. So here's On the left panel, you can see that red box is where we're looking, the northeast part of the caldera floor. And on the right are depth changes in color from 0 to 15 meters. So that's times 3, that's about 30 feet or 40 feet thick. So that's relatively thin. And then in contrast, we're now on the right map, you can see we're looking way to the north. This is where the thickest flows came out. They're up to 127 meters. So that's like over 400 feet. So that's 2/3 the height of the Space Needle. So imagine a pile of lava that thick that came out. So a lot of lava comes out in these eruptions, but it's so deep that it doesn't have any effect on the surface ocean. And I should have, when I was looking at the maps at the beginning, I should have mentioned that Axial Seamount, so it's 300 miles offshore, so it's far enough from the subduction zone that any activity out there doesn't have any effect on the subduction zone. So when there's eruptions out there, it doesn't increase our earthquake risk. It doesn't cause tsunamis. It's pretty benign. So just want to make that point. Okay, so let's see what those flows look like. This is some video from a remotely operated vehicle, some dives we made after the eruption, like 3 or 4 months after the eruption in 2015. So we're first going to visit those thin flows in the caldera. So these are very fluid lavas. Here's the edge of the flow. So the dark lava is the lava that just came out. Those yellowy areas are older seafloor that have some sediment on them. These are very fluid flows, so they come out, they inflate kind of like an air mattress where there's a crust on the top, but the interior of the flow is still molten, and while it's still molten, it drains out, so it leaves this crust. Some of it collapses, so there's all these collapse areas, and we're sampling some of that upper crust there. And as it's draining, it makes all these bathtub rings, and so it's really an amazing landscape of all these cavities beneath the crust. So that's a thin sheet flow, we call it. Now we're going to jump to the North Rift Zone and look at these thick flows that are very different. So this is pillow lava. Here it looks like some ancient seafloor, but actually this orange fluffy stuff is bacterial mat that has grown on the new lava flow because these thick flows cool over months to years even, and as this warm water is coming out of the flow, all these microbes can grow there, and they make this mat, and so it's kind of deceiving at first, but you can see we had that little suction sampler that sucked some of it off, and it was indeed black and shiny underneath. All right, so back to the inflation deflation story. All right, so we left off here, the 2015 eruption had just happened, and just before the 2015 eruption, this cabled observatory that I talked about at the beginning came online. At first, we didn't know how to connect it with our longer time series, but we eventually figured that out. So here's the cable route from Pacific City all the way out to Axial. This is all funded by the National Science Foundation, and it's operated. The cabled observatory is operated by a group at University of Washington in Seattle. And here's the end of the cable out at Axial Seamount. So there's a bunch of instruments all plugged in to the cable in various places, including seismometers. So now we have earthquake data and our pressure recorders. So we've got a number of those out there. So we can look at the two together, the earthquakes and the uplift. So, so after 2015, we saw that it immediately was inflating at a pretty high rate, and then from about 2017 to 2019, it seemed to be inflating at a pretty steady rate. And so, and the previous forecast had worked so well that I decided it was time to try to do it again, see if we can do it again. So here's our first eruption forecast window. And as soon as I did that, the rate of inflation decreased by about half. So once we figured that out, and it seemed to be holding that same rate, we extended the window. So this is late 2019, but then the rate of inflation kept decreasing. So it seemed like it was steady, but then it gradually was slowing and slowing, so that each time we seemed like we had a steady rate, we had to move this window to the right. But then it's kind of going off the page, right? So now it's 5 centimeters a year. That's pretty slow. So this is mid 2021. By the summer of 2023, it had almost stopped inflating. So, okay, I give up. This isn't working. So here we are, summer of or early fall 2023. But then it perked up again. So over a pretty short time, by the summer of 2024, it was inflating again at 25 centimeters a year. So, okay, I guess I should try to do this again. So we, that's the time when we made this latest forecast. So the current forecast is like the 5th or 6th try. So it hasn't been very successful this time. But there's kind of 2 separate questions. There's the question of, does this volcano have this repeated pattern? You know, it could still, the next eruption could still be triggered at about that same threshold, right? A separate question is, when are we going to get there, right? So it's my trying to do create a forecast window has not been working because the rate of inflation has been so variable. But it could still be a repeatable behavior. It's just that I got too ambitious about trying to say when it was going to happen. So we'll see. We won't really know until it happens. So since then, the rate has slowed again, but it's been pretty steady over the last year. So this is data through about a month ago. So it's still inflating at this steady rate. It's a little bit less than it was in the summer of 2024. But now we're up over the 2015 inflation threshold. So my feeling is it's going to happen sometime soon. I don't know if it's going to be by the end of the year or not. If not, then probably have to say, okay, another year, but we'll see. So, but here's the earthquake side of the story. So the blue is what we've been looking at, right? It kind of got flat and then it picked up again, and it's been inflating at about the same rate for the last year. So in red is the number of earthquakes detected per day. So right after the 2015 eruption, it was very quiet for a couple of years. And that's because during the eruption, there's a big deflation, right? So the stress in the crust above the magma reservoir gets relaxed. Oops. So big deflation, everything sort of relaxes, all the stress is relieved. So then it's reinflating, and even though it's at a very rapid rate, it takes a while for the stress to build back up, which is what generates earthquakes. So there's a couple of years with hardly any earthquakes. Then in about 2018, they start to pick up, but at the same time, the rate of inflation is decreasing, so it's sort of on again, off again. But then at the beginning of 2024, when we have this latest uptick in the inflation, the number of earthquakes really took off. Earthquakes, yeah. And so, you know, there have been a few days with over 1,000, 2,000, 3,000 per day, but then in between it drops back down to kind of more moderate levels. So here's the same thing, but now the red line is the cumulative number of earthquakes. So this kind of shows the rate. So, you know, it's gotten very steep on the right side. So, yeah, big change in 2024 when the whole system's sort of getting highly stressed and you know, I think preparing to fail. Eventually this crack is going to open up and feed the next eruption. So here's the long-term plot again. So we're above the 2015 threshold, but we may, just like the 2015 threshold was higher than 2011, we may need to go higher still. That's sort of what's been in my mind as I've made these forecast eruption forecast windows. I already made this point that, yeah, it could be inflation predictable, but I've just done a bad job of guessing when we would get there, but we'll see. And here's a comparison of the earthquakes before the 2015 eruption on the left and since the 2015 eruption on the right. So this latest uptick, we're up to an average of about 300 earthquakes per day. But before the 2015 eruption, it was up over 2,000. But the rate of inflation was also much higher then. So we're trying to weigh those two things. I don't necessarily think we need to get up to 2,000 earthquakes per day. But, right, so that's the point I just made. Okay, so coming full circle, this is what's happening out there that's behind all these headlines. I kind of like the bottom one the best because, you know, what this is all about for me is learning how volcanoes work. Axial Seamount is a great natural laboratory for learning about how magma is stored, what triggers eruptions, how we can improve our forecasting. And so we, you know, really hope that the lessons we learn there can be applied to other volcanoes that are pose more of a risk to people around the world. So I'm going to end there, and I'm happy to answer any questions you might have. Thanks.
Thank you.
Okay, yeah. Okay.
Go ahead.
Hi, my name is Dean. I got two items I want to. I missed the first part of your lecture a little bit, and so an axial seamount is just the underwater volcano, or is it something else?
Yes, it's an underwater volcano.
Okay.
Yeah, about 300 miles offshore.
Okay. Now, when Mount St. Helens blew, it was partly because there was a lot of pressure built up underneath it, right? So my question is, does deformation happen because of the gases that are built up due to the lava, or is it the actual physical lava that actually presses on the rock? And because there was a big explosion with Mount St. Helens, and of course it was so strong it could knock down trees at the other end of the valley.
Right. It's mostly the pressure in the magma, in the fluid magma. Yeah. So there's a big difference between Axial Seamount and Mount St. Helens, and it's the composition of the lava, the magma. So yeah, molten rock is magma when it's underground. It's lava when it's on top of the ground. So Axial Seamount is more like the volcanoes in Hawaii or Iceland. So the lava is very fluid. It's called basalt. Mount St. Helens is more like andesite or dacite. So it's much more viscous and has much more gas dissolved in it. And that combination makes it more explosive because Viscous means it's pasty, it doesn't flow as easily, so it's got more gas, but it gets trapped in there, and it essentially has to break the rock apart to get out. So it's the gas pressure that's more significant in terms of the character of the eruptions. Yeah, big explosive eruptions are the gas bursting out, basically breaking the rock open and pulverizing it and creating ash and so forth. Yeah,
so that defines the difference between underwater and land-based ones?
And it's more basalt versus dacite. So it's
Okay.
like Hawaii versus Mount St. Helens. Yeah.
Thank you.
Good question.
Behind you.
Yeah, this is Paul. I have a quake feed app on my phone because I just find it fascinating. And it seems like in the last week, something off the Oregon coast was a 5.4 app. And I have it kind of
Earthquake.
limited, only reporting 5s. And
Yeah.
it seems like there was another. So was that one right there?
It was, if you remember, at the beginning when I was showing the map offshore, so there's the Juan de Fuca Ridge, that's where the plates are spreading apart. South of there is the Blanco Transform, that's where plates are moving side by side. That's like the San Andreas Fault, but offshore. So that earthquake was at the southern end of the ridge, probably on the Blanco Transform Fault, because the Blanco has lots of magnitude 5 and 6 earthquakes, several a year. And yeah, so that I think that earthquake was on the Blanco, but it was, yeah, over a magnitude 5. So I could see it on our instruments at Axial Seamount. So it shook the seafloor enough at Axial to show up on our little pressure sensors and also our tilt meters. So it didn't do anything, but I could see the earthquake, shaking at Axial Seamount. Yeah.
Hi, this is Don. Up until a few years ago, I led an annual hike up in the Mount St. Helens area, and we usually turned around at the top of Harry's Ridge above Spirit Lake,
Yeah.
and there's a device there that measures something, and I asked about it, and they said it's measuring continental drift, and that it could detect a centimeter.
Uh-huh.
Is that right? That they really couldn't
Oh, yeah.
detect that?
So that's
small
probably
of
a GPS antenna. So that GPS is Global Positioning System. Yeah, that's what our phones have. That's where we can tell where we are. But fancy ones, you can put an antenna, and it gets data from orbiting satellites, and it can use those signals to locate itself on the Earth's surface super precisely. So these fancy ones, can be really less than a centimeter horizontally and not as good vertically just because of the geometry. But so when people are monitoring volcanoes on land, they do that a lot, use those GPS monitoring networks to do the same sort of thing we're doing with the pressure sensors. But yeah.
Hi, I'm Lucy. Is there the volcanoes in Hawaii created the islands? Is there any thought that this could have the potential to grow big enough, and on what kind of a time frame, thousands of years, to come up above and form a new island?
Yeah, good
Or
question.
chain of islands?
Yeah. So, good question. I should have had that map of the Northeast Pacific at the end here so I could refer to it. So, yeah, that same map I was showing at the beginning. So, Axial Seamount's on the Juan de Fuca Ridge, but it's actually just west of it. So, and it's this hotspot. So, a hotspot is a plume of magma that's coming from deep in the earth in one spot. Basically, there's one feeding Hawaii, there's one feeding Iceland, there's one feeding Axial Seamount, and if it's in the middle of the plate, like Hawaii, so the hotspot is kind of fixed in the mantle, and the plate is moving above it, right? So in Hawaii, there's a whole chain of islands because the hotspot is fixed, but the plate keeps moving, so it's kind of like a conveyor belt. You build an island and then you move it off, and so like the Big Island is the youngest Hawaiian island, and each one that's further from the Big Island is older and older. So at Axial Seamount, it's the same pattern. So there's Axial Seamount near the ridge, and to the northwest, there's a chain of seamounts that get older and older as you go away. And one of them was above sea level at one time because it has an eroded top. So this is Cobb Seamount. It's about, the top of it is now at about 50 meters depth. So, back when sea levels were lower, it was above sea level. But most of the other ones didn't grow that big. So it's capable of doing it. I don't know why Cobb grew bigger than the rest of them. Axial Seamount, the top of Axial Seamount is now 1,400 meters, so that's like 3/4 of a mile. So it's still pretty deep. It's hard to imagine that it's going to grow into an island, and its lifetime is probably hundreds of thousands of years, maybe 1 million years, kind of thing. So, yeah. Don't. If somebody tries to sell you beachfront property out there, don't buy it.
My name is Janet. Could you talk a little bit more about the way you're measuring the rise and fall? You said from pressure, but it seems like the ocean depth is variable and even day to day and over time.
Right.
I don't see how that works.
Yeah. It is kind of amazing. So, yeah, these instruments are on the seafloor, and you're right. There's waves, there's tides. So the raw data has the tides in it, and out at Axial Seamount it goes up and down about 1 meter, 3 feet. So the first thing we do is we convert the pressure measurements to equivalent depth, and then we subtract predicted tides. So then there's still some noise in there because the predicted tides aren't perfect, so there's some residuals from the tides, and there's also oceanographic signals because of the weather. The winds are kind of moving the ocean around, and it's piling up in some places and not in others. So there's definitely noise, but over a short time period, if you're catching some small event, you don't have to worry about that noise. You just see the signal, right? If we want to get rid of some of that noise, we can subtract one station from another because they have the noise is the same but the two stations. So then what we do typically is we have a station at the center of the caldera that measures the most up and down, and another station east of the caldera that measures the least. So if we subtract those two, we get most of the uplift signal without the noise. So, and that brings it down to about 1 centimeter of noise. Yeah. So amazingly, the waves all get filtered out at the bottom of the ocean because I think it's a spatial thing. You don't see individual waves at the bottom of the ocean. You see the tides, but not individual waves. Although, when there's storms out there, the data gets noisier for sure. I can see that.
Okay.
Yeah. Does that answer your question?
Thank you.
Yeah.
Okay, I'm Tom.
Okay.
One question I had, since the seamount is on the western side of the Juan de Fuca Plate, which is spreading away from the Pacific, while on the eastern side, as we all know, it's diving under the Pacific, diving under the continental plate,
Right.
and has stuck there. Do you think that an eruption at the western edge of the Juan de Fuca Plate would have the effect of reducing the pressure on the subduction zone that is threatening the big one?
No. But it wouldn't. Basically, the two things are too far apart to influence each other, and the plate is not that strong. And yeah, so anything that happens on the ridge is just its own thing, and anything that happens on the subduction zone is its own thing. They don't influence each other. Yeah, they're just too far apart. They're both, yeah, it's opposite sides of the plate, right? Yeah, so but they're related in that way.
I have a couple of questions, depending who else has questions. First of all, is there any, I mean, is this the same kind of volcano as the Yellowstone supervolcano? Does this teach you then anything about that in terms of how they operate, or is that a totally different kind of volcano?
That's a pretty different kind of volcano, yeah. I mean, it's Yellowstone is a hot spot, but it's in the middle of the continent, right? So it's really thick crust. It's the magma changes composition as it in the thick crust, and so yeah, it's more of a explosive type composition. And because the hot spot is there and it can generate so much magma, that's why it's a super volcano, because it can sit there for a long time and accumulate a whole bunch of magma and then have really big eruptions. But thankfully they don't happen very often, like every 600,000 years or something.
Right.
So yeah.
Another question is the earthquakes that you say, and there's an increase in earthquakes. What magnitude are we talking about?
Oh, yeah,
What,
good
what
question.
are the level?
Tiny, yeah. So most of the earthquakes are like magnitude 0, and maybe they get up to magnitude 2 or something. So you know, you can basically only detect them with seismometers. If you were standing there, you wouldn't notice them. During eruptions, there might be some a little bit bigger, you know, 3s and 4s, but they generally don't get too big. At volcanoes like this, yeah, you know, every volcano is a little bit different, and it depends on their setting. But generally, volcanoes have lots of small earthquakes from. That's a reflection of how the crust is responding to all this magma pressure underground.
Your second.
My name's David. What is the future for the Juan de Fuca Plate? Is it closing? Is it being dragged off to our coastline? Is it going anywhere?
Yeah, I think if you go back in geologic time, the animations I've seen is it used to occupy most of the Pacific, and it's been moving towards North America. And so, yeah, the Juan de Fuca Plate has gotten smaller and smaller and smaller. And, yeah, I'm trying to think of the time dimensions. You know, it's tens of millions of years. So, it's, but yeah, I think they are converging. So eventually, it's all going to go down the subduction zone, and then who knows what's going to happen after that? Be a different kind of plate boundary offshore.
Oh, this is Paul again. You know, you mentioned thermal vents, and obviously that magma coming up is creating that. Around the world, there's a whole interesting life forms that that are around those vents, does this area also have a number of those things that can be studied?
Yeah, I didn't talk about that at all, but Axial Seamount has lots of hydrothermal vents. Most of the big vent areas are around the edge of the caldera, where the caldera faults are sort of conduits for hot water coming up. So yeah, seawater seeps into the ocean crust. There's magma down there that's really hot. Heats up the water, and then as it gets more buoyant, so that hot water wants to make it back to the surface, and as it's because of all the pressure, the water can heat up to way above the boiling point at sea level. So boiling point at sea level is 100 degrees C. It can, at hydrothermal vents, it can be almost 400 degrees C. So, and water gets really reactive when it's that hot, and it as it's flowing through the rock, it dissolves a lot of the elements out of the rocks. And so that's why high temperature hydrothermal vents, they call them black smokers. That all that smoke is tiny mineral particles, so that the hot fluid is full of all these elements. It mixes in with cold seawater, and all those things that were dissolved precipitate into tiny little particles. And so that's what that smoke is, and that's why they build those big chimneys. Those are all made out of the minerals that are dissolved out of the rocks, and they're usually sulfide minerals, and there's lots of zinc and iron and copper and gold and silver and all kinds of stuff that's leached out of the lava rock that makes up the seafloor. So there's high temperature vents out there. And there's lots of low temperature ones too. It all depends on how efficient the hydrothermal conduit is. If it's closed off to seawater, it can stay really hot all the way to the surface. If there's a lot more mixing with seawater, then it turns into lower temperature, and that's what the animals like. So there's all this out there. There's completely different ecosystem that we didn't even know existed before 1979. And it's so instead of photosynthesis that we're familiar with on land here, it's chemosynthesis. So there's chemical energy in these vent fluids, and the bottom of the food chain are microbes that do little chemical reactions that yield energy. And then there's animals that are symbiotic with them, or eat them, so there's this whole weird ecosystem of animals that are making a living out of the chemical energy coming out of the vents. Yeah, so there's all kinds of tube worms and limpets and clams, and then bigger animals that eat them out there. So yeah, it's very cool.
This is Gwen Ellen. Can you real quickly tell us what attracted you to studying underwater volcanoes? I mean, besides the potential for headlines.
Yeah. Mount St. Helens erupted when I was in college. And that really got my attention. I was a geology major. Plus, it was my senior year. I had to do some kind of research project, and I finagled a way to volunteer at Mount St. Helens with the US GS. And this was after the big eruption, but it was I was there during the first dome building eruption. So before I knew it, I was helicoptering into the crater, and it was totally blowing my mind. And wow, this is really exciting. I want to do some more of this. So I worked there for a couple years after college, and then went to graduate school. And I didn't, the submarine part came because that's the job I got when I was looking for a job after graduate school. I had never done any marine work, but it turned out to be a kind of a perfect niche of kind of combining the land volcanology with submarine volcanoes, where we knew a lot less. And so it's been fun because because we knew, it's a lot harder to tell what's happening at the bottom of the ocean. So lots of opportunities for discovery and finding out new things. So it's been great. Yeah.
Okay. Thank you, Dr. Chadwick. Thank you so much.